let's continue our discussion with temperature variation with resistance. So the resistivity, where'd my pen go? Resistivity of all materials depend on temperature. And at very low temperatures, some of these materials can become superconductors. Okay, so that's at low temperatures. And at increasing temperatures, the resistivity of conductors increase. Okay, so low temperatures, resistivity decreases. At high temperatures or increasing temperatures, resistivity will increase. Okay, so this is the basic concept that I am going to be looking for you guys to know, but I'm not going to go into the mathematical details of this. Okay, it is in the textbook, but I am not worried about it. Okay, I just want you guys to understand low temperatures, resistivity decreases. Higher temperatures, resistivity will increase. Okay. Let's talk about electric power. So we've talked about power in the past, and that is power with motion, right? We talked about with, let's see, with work, I believe. That's when we talked about it, right after work. And for electric power, it's going to be the rate at which energy is moved, okay? So power is going to be equal to current times voltage. Okay, so this is equal power. And we can rearrange this a few different ways, as you may have guessed by looking at this page. We have power can also be equal to V squared over R, and it can also equal I squared times R. Okay, and this is because we have three different variations because V is equal to IR. So we can plug these in almost every which way to find power, okay? So I just want you to be aware that there's not one particular equation. You can kind of manipulate them so we can solve for power with whatever our inputs are. Okay, so here is an example, and my examples from now are examples that you will see on the homework assignments. So this one says, what is the power of a 1 times 10 to the second megavolt lightning bolt having a current of 2 times 10 to the fourth amps? So I'm looking for power given voltage and current, okay? And this M here is mega, and that is times 10 to the sixth, okay? So we just found that power is equal to, and we have a few different variations, so let me go back and look. We have voltage and current. So that's actually going to be our first one. Power is equal to I times V. Okay, so we can plug those guys in. Current is 2 times 10 to the fourth amps. Our voltage is 1 times 10 to the second, and this is megavolts, so we'd have to say times 10 to the sixth volts. Okay, so let's throw that into our calculator. We have 2 times 10 to the fourth, whoops, times 1 times 10 to the second times 10 to the sixth. I'm sure some of you can do this in your head, but I'm going to trust my calculator. As long as I put it in right, we've got 2 times 10 to the 12th, and this is power is in watts. Yeah, I can double check. I didn't put that on the slide. Whoops, my bad. Let me look really quick. Power. I don't want to tell you guys wrong. I don't know why I didn't put it on the slide. Yeah, watts. Okay. I just didn't want to steer y'all wrong. Okay. So now we have our power in watts. Okay. All right, so let's look at another example. How many watts does a flashlight that has 6 times 10 to the 2, or 10 squared, coulombs pass through it in 0.5 hours or half an hour, use if its voltage is 3 volts. Okay, so this one seems a little bit more complex, but we can do this. So we have time here, or delta T. We have our charge, delta Q, and our voltage, V. Okay, and we're looking for watts, so we're looking for power again. Okay, so what we'll need to do is, with our charge that's being passed through and our time, we can find our current. So remember, current is equal to delta Q over delta T, and that will be 6.0 times 10 squared C, or coulomb, divided by 0.500 hours. Whenever we're trying to find watts, that is in joules per second, equals a watt. So we need to convert this hour into seconds. Okay, so bear with me here. We have 1 hour, and in 1 hour we have 3,600 seconds. Okay, that's something that I've just memorized over my time, okay? All right, so let's go ahead and do that. 6 times 10 squared, and then divide that by 0.5 times 3,600, and we get 0.333, and this is coulomb per second. So this is our current. Okay, this is a weird U. And then we are trying to find power. So power we just found was V times I, right? Yeah, I times V. So we can plug our values in, 0.333 coulombs per second, times our voltage, 3.0 volts. So then we do that, and we actually get 1 watt. Okay, so 1 watt of power. All right. Okay, again, I will have a question similar to these last two on your homework. Okay, now I just wanted to introduce the concepts of direct current and alternating current. So direct current, or DC, is the flow of electric charge in one direction, okay? So this means that it's constant in time, so not changing in time, okay, with time. Stays the same. So this first portion here, let me split these up. This top half shows DC current, or I should just say DC, sorry. That is DC. Okay. So again, it's constant in time. We can see that the voltage stays the same and the current stays the same. Okay. So we have a steady stair. This must be a typo. It has a steady current and voltage. So steady or constant. Okay. Then we have alternating current, or AC. That's what we see here. This is AC. The electric charge periodically reverses direction. Okay, so we'll have some, trying to think of a simple term here. We'll have some sort of, this looks like a sinusoid. If you guys have heard of that, I'm not sure that you have, but see how it varies. So it goes from a positive here to a negative, then to a positive, okay? So we have some sort of alternating current due to the current and the voltage changing, okay? So it'll go from positive to then a negative due to that change in electric charge. So our Q would go plus then minus, then plus then minus, okay? Varies periodically, and example, I should say this is an example, would be commercial or residential power, okay? And you can get some more info in the textbook from that. There's also some other information in the textbook regarding some real life applications. If you guys are interested, feel free to look at that. But other than that, this is all we have for now. Next time we'll be looking at circuits and DC instruments, and also capacitors in series and parallel, and what that all means in the next lectures, okay, in the next module. So for now, that'll be it. And then, yeah, that's all I have to say. So thanks, and we'll see you next time.